Good morning, everyone. Let's get started. So in the previous classes, we were talking about degraded broadcast channels, and in the last class, I started discussing Gaussian broadcast channels. Right. So the two-user Gaussian broadcast channel is the following, where you have a single transmitter who's sending XN, and two receivers, one who gets Y1N and the second receiver gets Y2N. Each of the receivers essentially sees a corrupted version of Xn, and this is corrupted by additive white Gaussian noise of variance sigma 1 square over the first channel and sigma 2 square over the second channel. And without loss of generality, we can assume that sigma 1 square is strictly less than sigma 2 square, which implies that user 2 is degraded with respect to user 1. So no matter what kind of a broadcast channel it is, even if you have a general k-user Gaussian broadcast channel where each user sees an independently corrupted version of Xn, and the corruption is Gaussian, such a channel is always stochastically degraded. Okay, and since it is stochastically degraded, we know we can compute the capacity or the capacity region of such a broadcast channel. And in the last class, I said that the capacity region of a two-user Gaussian broadcast channel with input power constraint of P and noise variances of sigma 1 square and sigma 2 square over the first channel and the second channel respectively is given by the set of all R1, R2 which satisfy the following constraints. So R1 is less than or equal to half log 1 plus alpha P by sigma 1 square, and R2 is less than or equal to half log 1 plus 1 minus alpha P by alpha P plus sigma 2 square for some alpha which lies between 0 and 1. All right. And for this, we'll see a separate achievability and a converse proof. The achievability is essentially just superposition coding. And really the way the coding works is that since you have a total power constraint of P at the transmitter, what you do is you allocate alpha P of the power for the codebook of user 1, and 1 minus alpha times P of the power to the is allocated to the codebook for user 2. Right, and then you just add code words from this codebook and transmit it. User 1 is able to decode both code words as long as essentially R1 plus R2 is less than or equal to 1 plus P over sigma 1 square. And in particular, if R1 is less than or equal to half log 1 minus alpha P by sigma 1 square and R2 is less than or equal to this, then user 1 is able to decode correctly. User 2 essentially decodes his code word by treating the first code word, that is a code word for user 1, as part of the noise. Right? So you have yn equal to x1n plus x2n plus zn. So in particular, yin for I equal to 1 or 2 is x1n plus x2n plus zin. And so what user 2 can do is you treat x1n plus z2n as the noise, effective noise, and then you try to decode x2n. And decoding succeeds as long as R2 is less than or equal to this quantity. So the total effective noise variance is the variance of x1 and plus the variance of z2, which is alpha p plus sigma 2 square. And a total of 1 minus alpha times P of the power is allocated for the codebook of user 2. So x2n has a power of 1 minus alpha times P. So it's essentially like a point-to-point AWGN channel, and decoding succeeds as long as the rate is less than or equal to this. So this turns out to be the capacity of such a channel. What user 1 does, it uses a similar approach to first decode x2n, and then you remove x2n from, since x2n has been decoded, you remove it from y1n. So the effective channel for decoding x1n is just x1n plus z1n. And that decoding succeeds as long as the rate is less than the capacity of this new channel, of this effective channel. And the capacity of that channel is just this quantity, half log 1 plus alpha p by sigma 1 square. Right? So decoding is done in a successive fashion. We first decode x2n, and user 2 is all user 2 can do is just that. So he cannot decode x1n. But since user 1 sees a better channel, it first decodes x2n and removes the component of x2n from the received signal and then decodes x1n. Right? So this is the superposition coding rate region, and it turns out that this is the capacity region for the Gaussian broadcast channel. So in the last class, I just gave a sketch of the achievability, and in this class, we'll see a proof of the converse. So in fact, no matter what code you use, if you want to ensure that the probability of error is vanishing in n, then R1 must be less than or equal to this, and R2 must be less than or equal to this for some alpha between 0 and 1. So irrespective of what kind of a decoder you use, irrespective of how you construct your code books, these rates must satisfy these constraints if you want the probability of error to be small. Okay, so we'll see a proof of the converse, and then I'll make some general comments about maybe more general degraded, more general broadcast channels, some special cases, and then maybe from the next class onwards, we'll start looking at fading channels and how various kinds of fading can lead to different types of channels, and how do you characterize the capacity regions of such channels. Okay, so before we proceed, are there any questions?
Sir, this is Girish.
Yes, Girish.
Sir, I just have, a small question, sir. Here, whenever we are talking about degradation and power constraint together, are we talking with respect to the degradation in power, or are we talking with respect to degradation in the channel capacity?
No. So the degradation is always with respect to the channel, right? So in some sense, you have right. So in a broadcast channel, you have a single sender who sends xn, and then this goes through some channel which is where you can have arbitrary correlations, and you have user 1 getting y1n and maybe user 2 getting y2n. Right? So there are two aspects of this. One is the channel itself, which is how xn gets corrupted to get y1 and y2, and the second is whatever power constraint or whatever cost constraint that the transmitted signal has to satisfy. Right? So this is the cost or power constraint. Right, so this is fixed, but these constraints do not affect the channel itself. Right, so of course, by changing the power or the cost constraint, the capacity of the channel changes, but this joint distribution, that is the distribution of y1n and y2n given xn, p y1 y2 given x. So this is independent of what kind of a power constraint you impose. Right? So this is something which is part of the system design at the transmitter, whereas this is the environment itself. And degradedness refers to how the environment behaves. What you say is that y2 is a worse copy than y1. So in some sense, y2 is worse than y1. So there are again different ways in which y2 can be worse than y1, and that is why we have different notions of one channel being stronger than the other. We've seen degraded channels, we've seen less noisy channels and more capable channels and so on. But these are characteristics of the channel and not and have nothing to do with the cost or the power constraint.
Right.
Right. Okay. Any other questions? Right. So we've seen the achievability part of that you can construct codes which achieve any rate satisfying any rate pair satisfying these constraints. So now let's see that it's impossible to do better than this. Okay. And for this, I mean, to prove the converse, we look at the physically degraded Gaussian broadcast channel. So to prove the converse, right? So this is the case where you have xn, and then this is passed through an AWGN channel. So let's call this Z1n to get Y1n. This is what receiver 1 sees. And then what receiver 2 sees is a corrupted copy of Y1n itself. So let's call this Z2 tilde n. So Z1n is IID Gaussian with mean 0 and variance sigma 1 square. And Z2n is Gaussian with mean 0 and variance sigma 2 tilde square, where sigma 2 square is sigma 1 square plus sigma 2 tilde square. Okay. So the effective channel from xn to y2n is an AWGN channel with mean 0 and variance sigma 2 square. But this can be obtained by corrupting y1n with the received vector of receiver 1 by a Gaussian with mean 0 and variance sigma 2 tilde square. Okay, so we'll prove a converse for this, and then since the capacity region is not affected by so the capacity region of any stochastically degraded channel is the same as the corresponding physically degraded broadcast channel, we can just conclude that we can just find out that the capacity is what the capacity is. So for this channel, let's try to derive an outer bound. Okay, and the initial part, the technique that we will use is essentially similar to what we did for the binary symmetric broadcast channel. So as always, we start with the entropy of the messages. So NR1 is the entropy of the first message. You're transmitting NR1 information bits to user 1. And I claim that h of M1 is equal to h of M1 given M2. Why is this true?
So both are independent. So
messages are independent. So the conditional entropy of M1 given M2 is the same as the entropy of M1. So messages are independent. Okay, great. So once we have this, I'll just introduce another term, h of M1. If I add and subtract h of M1 given Y1 M2, then basically h of M1 minus h of M1 given M2 minus h of M1 given Y1 M2 is just equal to this mutual information. And the remaining term is a plus h of M1 L1 given Y1N M2 L2. Okay, and then I just use Fanos inequality to upper bound this conditional entropy. Since You want so given M2, user 1 should be able to recover the message reliably given from Y1. Right? So it's just I use Panos inequality. Right? So the first term is left as it is, but the conditional entropy of M1 given Y1 and M2 is less than or equal to H2 of PE plus PE times NR1. Right? Where PE is well, you can replace it by the probability of error of decoding M1 from Y1 and M2, which is upper bounded by the probability of error of decoding both M1 and M2. Okay, so I have an upper bound on NR1 in terms of the mutual information between M1 and Y1n given M2 plus some quantity which is very small. Since the probability of error tends to 0 as n tends to infinity, this overall quantity is at most n times some epsilon for some small epsilon greater than 0. Okay, and so the term that we really need to care about is this first term. Right? As long as we can show that this is less than or equal to whatever that half log 1 plus alpha p by sigma 1 square, we are done. So similarly, I mean, just using an identical set of steps, we can also get NR2 to be less than or equal to the mutual information between M2 and Y2n plus some small quantity. So H2 of PE plus PE times NR2. Okay. So now let's try to get bounds on each of these mutual informations. All right. So let's start with the definition of the mutual information in terms of the differential entropies. Note that Yn is a continuous random vector, whereas M2, L2 is discrete. Okay, so you need to be a little careful over there. So this is the difference between the differential entropy of Y2n and the differential and the conditional differential entropy of Y2n given the second message M2. All right. So let's start with Y2n. Right. Okay, so Y2n is essentially xn plus z1n plus z2 tilde n. Okay, so what can you say about the variance of Y2n? Or the variance of, let's say, Y2 of I for any I. Note that xn, z1n, and z2 tilde n are all independent of each other, right? So the variance of Y2 is the sum of the variances of each of these.
Yes.
Right? So what is that equal
Yes.
to?
Sigma 2 square tilde. Sigma 1 or 2 square.
Sigma 1 square plus sigma 2 square plus plus p, right?
P, yes, sir, for xn.
Right. Okay. So since this is the variance, we know that the differential entropy of any random variable is at most so the differential entropy is maximized for a given variance. The differential entropy is maximized when the random variable is Gaussian, right? So this differential entropy is at most n times half log 2 pi e times p plus sigma 1 square plus sigma 2 tilde square, which is but the sum of these two, this is just sigma 2 square. Right, so let me just write this as p plus sigma 2 square. Okay, and the second term we'll leave it as it is for now, h of y2n given m2 l2. Okay. So far so good. So let's now try to get some bounds on h of y2n. Let me call this equation 1. Now look at h of y2n. Sorry, y2n given m2 l2.
Sir,
Yes.
sorry to stop, but
Uh-huh.
for the x, are we considering the power like power constraint to prove the converse, like p, which
Yes.
we are saying that power is less than or equal to np.
Exactly. Yes. Yes.
Acha, okay.
So you need to take that into consideration, right? So you know that the xn has to satisfy a power constraint of p.
Yes.
So automatically that constrains the entropy of yn. If there's no such constraint, then the differential entropy can be infinite for all we know.
Yes. Yes.
Right?
Yes.
Because here the alphabet is the set of reals, right? There's no, you need some kind of a constraint,
Yes, sir. I get.
right? Okay. So let's look at h of y2n given m2l2. I claim that this is less than or equal to h of y2n. Why is that true?
Conditioning reduces entropy.
Listening.
Yeah, so exactly. So conditioning also reduces differential entropy. But h2 of y2n, as we've just seen, is less than or equal to half log 2 pi e times p plus sigma 2 square. Okay. Now let's see if we can get a lower bound on this. So this is upper bound. This is lower bounded by h of y2n given m2 and m1, right? Using the same argument that conditioning can only decrease the differential entropy. Okay, but this is equal to h of y2n given m2, m1, and xn. Can someone tell me why?
As m1 is dependent on xn.
It's not exactly true. So I'm saying that this is an equality, right? It's not an inequality. So what can you say about xn in terms of m1 and m2? So given m1 and m2, is there any uncertainty left in xn?
No, sir.
No, sir.
No, right? Because the two messages together, they exactly uniquely determine the code.
Yes.
There's no additional randomness. So that
So
is why I
after,
can.
yes, sir, after adding this, there is no change in entropy of this one.
Exactly. So since xn is a deterministic function of these two,
Yes.
it's basically just equal to this, right? And vice versa. So xn uniquely determines. Okay. So m1 and m2 uniquely determine xn, but it's not always true that xn uniquely determines m1 and m2 together, because it's possible that two pairs of messages could correspond to the same code word, but the other way is not true. Okay, so this is an equality. Now this, I claim, is also equal to h of y2n given xn. Why is that true?
Since M1 and M2, they can be replaced with Xn, since Xn will have both the messages.
So that's what, right? So it's possible that two different sets of messages, two different pairs of messages could map to the same code word. It's a bad code book, but doesn't matter. Potentially they could map to the same code word. And in which case, if that is the case, then obviously xn does not uniquely determine m1 and m2. So what is the structure of the joint distribution of these three? Right? Can you say something? So here, in some sense, I'm saying that if you condition on xn, then y2n doesn't really depend on m1 and m2. Is that the case?
Sir, by writing this means last one term, it like it shows that this one is not depending, but how we can relate this?
So m2, but see, what is actually transmitted through the channel is xn, right?
Yes, sir.
So can I say that this forms a Markov chain?
Yes, sir, we can say.
All right. Because conditioned on xn, yn is independent of m1 and m2.
Yes, sir.
All right. Because the corruption to the channel, the way you're getting yn from xn, is independent of what the actual messages are. Right? Because this is because yn equal to xn plus z1n, y2 is xn plus z2n, and z2n is independent of everything else. So therefore, this conditional differential entropy is equal to this conditional differential entropy. All right.
Yes, sir.
But what is this equal to? This is just h of z2n, right? Or in my way, it's z1n plus z2 tilde n. Correct? Which is what? What is the differential entropy equal to?
2 pi e sigma 1 square plus sigma 2 square tilde.
Yeah, so
Yes.
or half log 2 pi e sigma 2 square. Correct? So h of y2n is somewhere between half log 2 pi e sigma 2 square and half log 2 pi e times p plus sigma 2 square. Okay, so let us say that, so let's say that h of y2n given m2 L2 is equal to, so this is some number. This is going to be h of y2 given m2 is going to be some number between this number and this number, right? So something in between. So this is equal to half log 2 pi e times some alpha p plus sigma 2 square, right? So when alpha equal to 0, you get this number. When alpha equal to 1, you get this number. So the correct value for a given h of y2 given m2 will be this for some alpha between alpha between 0 and 1. Right? Since this is between this and this, you can always find an alpha such that alpha between 0 and 1 such that h of y2 given m2 is equal to half log 2 pi e times alpha p plus sigma 2 square. Okay, so therefore now if I plug this back in equation 1, I'll get that the mutual information between m2 and y2n, so this is less than or equal to half log, I had 2 pi e times p plus sigma 2 square p plus sigma 2 square minus this quantity. So I can just say that this is half log 2 pi e times alpha p plus sigma 2 square. 2 pi e and 2 pi e cancels. So this is half log alpha p plus sigma 2 square plus 1 minus alpha times p. Right? So I'm just writing p as 1 minus alpha p plus alpha p plus sigma 2 square, which is just half log 1 plus alpha p by half log 1 minus alpha p divided by alpha p plus sigma 2 square.
Sir, isn't it n by 2 log 1 plus
Right,
minus
good point.
alpha 2?
So there I'm missing an n, thanks for pointing it out. So it is n times half log of this. So the mutual information between m2 and y2n is less than or equal to n times this quantity. Okay, so this is one part, right? So now let's look at the other quantity, right, which is the mutual information between m1 and y1 given m2. Right? So this is just again by expressing the mutual information in terms of the conditional differential entropies. This is just h of y1 given m2 minus h of y1 given m1 and m2. And exactly as we did before, h of y1 given m1, m2 is equal to h of y1 given xn. Right? So this mutual information is equal to h of y1 given m2 minus h of y1 given xn. Okay, but we know that h of y1 given xn is basically h of z1n L2 minus h of z1n L2 minus this is just half log 2 pi e times sigma 1 square. Okay, so we have this. Now what we want is a bound, at least an upper bound on h of y1 given m2. Okay, but what do we know? We have assumed that h of y2 given m2, this is equal to half log 2 pi e times alpha p plus sigma 2 square, right? Or let me instead write it in the following way: half log 2 pi e times alpha p plus sigma 1 square plus sigma 2 tilde square. All right, so we know that this is equal to this for some alpha between 0 and 1. But now what I want is h of y1 given m2. Right? But the observation that we need to make over here is that y2n is equal to y1n plus z2 tilde n. Right? So y1 is corrupted by z2n to give you y2n. Right? And this is Gaussian. Right? So this is so we need a bound on on the entropy, on the differential entropy of y2n given m2, but we already know what is h of y1 given m1. Sorry, we want h of y1 given m2. We know h of y2 given m2, and we know h of z2. Right? We want this. Want h of this given m2. We know the entropy of this given m2. We also know the entropy of z2 tilde given m2, because z2 and m2 are independent of each other. The noise is independent of the message. So this is half log 2 pi e sigma 2 tilde square. All right. Now, in the case of the binary symmetric broadcast channel, at this point we had used Mrs. Gerber's lemma, right, to get the entropy of y2 given m2 from the entropy of to get the entropy of y1 given m2 from y2 given m2. And here we're going to use a very similar approach, except that we can't use Mrs. Gerber's lemma. That works only for the BSC. But for AWGN channels, we already know something. So what we're going to use is the conditional entropy power inequality. The conditional entropy power inequality says that 2 to the 2 times h of y2 given any random variable. So in this case, m2 by n. This is going to be always greater than or equal to 2 to the 2 times h of y1 n given m2 L2 by n plus 2 to the 2 times h of z2 tilde n given m2 divided by n. Or if you want to look at it in terms of the entropy power, this divided by 2 pi e is greater than or equal to this by 2 pi e, this divided by 2 pi e. Okay, so what we want is an upper bound on h of y1 given m2. We know this term, what this is. This is h of y2 given m2 is half log 2 pi e times alpha p plus sigma 1 square plus sigma 2 tilde square. And this is half log 2 pi e sigma 2 tilde square. So that makes our job easier. So 2 to the 2 raised to the entropy by n is equal to this. Sorry, I'm always missing n here. So this is 2 to the 2 raised to n times half log 2 pi e alpha p plus sigma 1 square plus sigma 2 tilde square divided by n. So the n cancel, the 2 and 2 cancel, 2 pi e. So 2 raised to the log something is just this quantity itself. So this is equal to 2 pi e times alpha p plus sigma 1 square plus sigma 2 tilde square divided by 2 pi e. That's the left hand side. The right hand side is 2 to the 2 raised to h of y1n given m2 L2 divided by n divided by 2 pi e plus this entropy power just turns out to be sigma 2 tilde square. So this is half log 2 pi n times half log 2 pi e sigma 2 tilde square. Again, the n and the 2 and half cancel, and this turns out to be 2 pi e sigma 2 square divided by 2 pi e. So if I take the sigma 2 tilde square on the left hand side, this sigma 2 tilde square and sigma 2 tilde square cancel. I have alpha p plus sigma 1 square to be, so this is the entropy power or an upper bound on the entropy power of y1 given m2. So 2 to the 2 raised to h of y1n given m2 by n by 2 pi e. So this is upper bounded by alpha p plus sigma 1 square. Okay, so if I take 2 pi e to the left hand side and take log on both sides, I get 2 to the h of y1n given m2 L2 divided by n is less than or equal to log 2 pi e times alpha p plus sigma 1 square or h of y1 given m2 is upper bounded by n times half log 2 pi e times alpha p plus sigma 1 square. Okay, so now we have an upper bound on h of y1 given m2. We can now plug this back in here. So we know we have an upper bound on h of y1 given m2. So the mutual information between m1 and y1 given m2, this is less than or equal to n times half log 2 pi e times alpha p plus sigma 1 square minus n times half log 2 pi e sigma 1 square, which is simply half log 1 plus alpha p by sigma 1 square. Isn't it? Right? So note that throughout we didn't make any assumption on what the decoding scheme was or how the codebook was constructed. The only assumptions we made were about the channel, which is Gaussian. It's a physically degraded broadcast channel, and that the power constraint at the input is equal to P, right? And that led us to an upper bound on the variance of X, and therefore a variance on and therefore the variance of Y2. Right? So now we have upper bounds on both of these mutual informations. So n times R1 is less than or equal to this mutual information, which is n times half log 1 plus alpha p by sigma 1 square plus an upper bound on that conditional differential entropy, conditional entropy, which is h of PE plus PE times NR1, right? And therefore, since the probability of error is vanishing in n, R1 should be less than or equal to half log 1 plus alpha p by sigma 1 square plus some quantity which is vanishing in n. Right? If the probability of error is vanishing in n, then this quantity divided by n should also be vanishing in n. Okay, and similarly, we have R2 to be less than or equal to half log 1 plus 1 minus alpha times p divided by alpha times p plus sigma 2 square plus little of 1. All right. So this gives us the capacity region for the two-user Gaussian broadcast channel. Right? We've proved both an inner bound, which can be achieved using superposition codes, and an outer bound, which basically made use of the entropy power inequality and the standard techniques that we've used so far to prove converses. Right? Any questions? Okay, so this completes our discussion of the Gaussian broadcast channel. Now there are some more minor extensions, so I will not prove anything. So some of these results can be extended to the following cases. So one case is, so we assume that there are only private messages. So we have a message M1 which is intended for user 1 and M2 for user 2, which need to be conveyed. We have M1, L1, M2, L2, which is encoded to xn and passed through the broadcast channel. User 1 gets y1n, user 2 gets y2n, and from this user 1 has to decode to get m1, and user 2 has to decode to get m2. All right, so we assume that this is degraded. Right, but we assume that m1 and m2 are independent of each other, right? Now, what if in addition to this, you also have a common message? Right, suppose in addition there is also an m0, maybe this has L0 bits. Right, so there are three messages, m0, m1 and m2. User 1 has to decode m1 and m0. User 2 wants to decode m2 and m0. Right? You don't really care whether user 1 can decode m2 or not, and you don't really care whether user 2 can decode m1 or not. Right? It doesn't matter whether they can decode or whether they cannot decode. It doesn't really matter, at least for this particular problem. And so m0 is, so the rate of this message is r0. For this, the rate is r1, and for this, the rate is r2. So in this case, what is the best r0, r1, r2 that you can achieve? What is the capacity region of this particular degraded broadcast channel? We've seen that if you did not have any common message, then the capacity region is r1 is less than or equal to I of x y1 given u, r2 is less than or equal to I of x, sorry, I of u y2, and r1 plus r2 is less than or equal to I of x y1. Right, so this is essentially the superposition coding inner bound. Right, from this we can, I mean, it's pretty easy to at least get an achievability result. So if in addition you want to decode message m0, if both of them have to decode m0, then obviously it means that in the superposition coding scheme, you want user 1 to be able to decode all the three messages first. So you first, what user 1 does is that it first decodes the exact code word. So all the three code words m0, m1, and m2. So r0 plus r1 plus r2 should be less than or equal to x y1. User 2 should be able to decode both m0 and m1. So therefore r0 plus r2 should be less than or equal to this mutual information. And having decoded m0 and m1, or having decoded m2, you should be able to decode m0 and m1. So r0 plus r1 should be less than or equal to this. So even if you have an additional common message which both users have to decode, the achievable rate region using superposition coding is given by this. r0 plus r1 is less than or equal to this, r0 plus r2 is less than or equal to this, and r0 plus r1 plus r2 is less than or equal to this. As long as your r0, r1, r2 are satisfy these constraints, the probability of, you can construct a superposition coding scheme for which the probability of error of decoding all the three is vanishing in n. All right. So this is the case where you have a common message also. So here M0, M1, and M2 are all independent of each other. Okay, so this is just a simple generalization. Now, similarly, if you have more than two users, so if you have a general K user degraded broadcast channel, then the capacity region is given by the following. So we're looking at a K user degraded broadcast channel where you have the following Markov chain. So X, Y1, Y2, up to Yk, this forms a Markov chain. So Y2 is degraded with respect to Y1, Y3 is degraded with respect to Y2, and so on. So Yk is degraded with respect to all of these. Okay, so in this case, the capacity region is the following. Region is the set of all R1 to Rk such that, so unlike the two user broadcast channel, unlike the two user case, for K users, so for two users, you needed one auxiliary random variable. In this case, you need K minus one auxiliary random variables. Let's call them U2, U3 up to UK. So you have K minus one auxiliary random variables, and the rate constraints that need to be satisfied are that R1 should be less than or equal to the mutual information between X and Y1 given U2. R2 should be less than or equal to the mutual information between U2 and Y1 given U3, and R3 should be less than or equal to the mutual information between U3 and, this should be Y2, Y3 given U4, and so on. So in general, Rk is less than or equal to the mutual information between Uk and Yk. All right, this is specific to the degraded K user degraded broadcast channel. Rk minus 1 is less than or equal to the mutual information between Uk minus 1, Yk minus 1 given Uk. So in some sense, user K, who sees the worst channel, is only able to decode UK, is only able to decode his message, MK. The K minus 1th user can decode both message MK and message MK minus 1. The K minus 2nd user is able to decode his own message as well as the K minus 1th message as well as the Kth message, and so on. So user 1 is able to decode all the messages, his own message and user 2's message, user 3's message, and so on, all users' messages. Okay, then so this is again, it's a generalization of the superposition coding scheme for K users. Okay, so this turns out to be the capacity region of the degraded K user broadcast channel. Okay, but in general, if the channel is not degraded, then the capacity region is unknown. All right. So let's stop at this point. Any questions?
Sir, this is Girish.
Yes, Girish.
Sir, you have said that like last statement, sir, if the channel is not degraded, then the capacity is unknown.
Yes.
Sir, may I know why so, like, sir?
It's a very, very hard problem, and people have still not been able to solve it. So there are general inner bounds, there are outer bounds. So there are achievability proofs, there are converse proofs, and the two in general can give different rate regions. So there are broadcast channels which are non-degraded, for which we do not know what the capacity region is. We don't know what is the best that can be done.
Right, sir.
All right. So it's a very, very long-standing open problem, open for more than like 30, 40 years now. So if anyone is able to solve, I mean, even for 3 users, if actually, in fact, even for 2 users, even for the 2-user non-degraded broadcast channel, if someone finds the capacity region, the complete capacity region, then that itself would be a great breakthrough. But in many cases, it suffices. So we know the capacity region for the degraded broadcast channel, and you just try to apply that.
Right, sir.
All right. Okay, then. So this concludes our discussion of broadcast channels, degraded broadcast channels in particular. From the next class, we'll start talking about fading channels, and we'll see that throws up interesting new problems. Okay, so let's stop here, and we'll continue in the next class.